All right, guys, lecture video number 3 here. Today we're going to be talking about isotopes. Now, you might have heard about an isotope in the past. You might have heard about something called carbon-14, for example, right? Carbon-14 is that specific isotope that archaeologists and anthropologists will use to help actually carbon date. You might have heard of carbon dating before. Carbon-14 is a specific isotope of carbon. Carbon's an element, but elements have specific isotopes, consisting of them. Now, for example, when it comes to an isotope, maybe specifically of carbon here, this is the specific isotope notation that I want you guys to know and understand here. There's 3 main things associated with isotope notation. First and foremost is the atomic symbol itself, right? It's the letters, the 2 or 1 letters that you see on the periodic table and that you're going to see very, very consistently going forward. So the atomic symbol. In the upper or in the bottom left-hand side here is going to be the atomic number. Okay, atomic number, again, is just another piece of the puzzle that comes directly from the periodic table, right? Atomic number is always going to be the same for that specific element. So if I've got carbon, that's never going to change. Now, what will change specific to whatever isotope we're talking about is the mass number. So this upper left-hand corner number here, this mass number, again, mass number, if you remember, is the number of protons plus the number of neutrons. That's it, okay? That's what we talked about at the very, very end of last video. Again, this mass number, based on what isotope you're dealing with of that element, can and most likely will change. Now, getting into some of the nitty-gritty here of isotopes. Isotopes are atoms of the same, just with a different number of neutrons, and that's truly it, right? We've kind of talked about the 3 different types of subatomic particles, right? We've talked about protons, we've talked about neutrons, we've talked about electrons. Now, when you change the number of protons in an atom, it changes the atom's element, right? So, for example, I have some atom in front of me, right, that I'm able to manipulate, and I've got 6 protons inside of that atom. Well, if I remove 1 proton from that atom, going from 6 down to 5, that's no longer going to be an atom of what was originally carbon with 6 protons, and now has 5 protons. 5 protons means I've got an atom of borons. Whenever you change the number of protons of something, you are changing the atom that sort of element is made up of. Now, if I change the number of neutrons, that is what gives rise to isotopes. Therefore, when I have a different number of isotopes, the mass number and atomic weight ends up changing, right? They end up being different. So, for example, carbon-14, carbon-14, and carbon-12 are isotopes of each other. They're both carbon. They're both atoms that have 6 protons in them, right? The only difference is that carbon-14 has a mass number of 14, meaning that there's 2 more neutrons, and carbon-12 has a mass number of 12, meaning it has 2 less neutrons. Okay, so that's it. It's just a changing in the number of neutrons. This is a good little graphic here that kind of shows you that exact same principle here, right? So I've got 3 different isotopes of potassium, potassium-39, potassium-40, and potassium-41. Notice how, with all these examples here, my number of protons remains the same at 19. My number of electrons remains the same at 19. But the only difference here is that I have an increasing number of neutrons. From 20 at 39, potassium-40 has 21, and potassium-41 has 22. Okay. Now, the biggest thing here is to make sure we can remember that we get the 39, the 40, and the 41 from adding up our number of protons and our number of neutrons. So 19 plus 20 is going to give us 39. Okay? 19 plus 21 is going to give us 40. 19 plus 22 is going to give us 41. Okay? So again, remembering that the mass number is the combination, right? The addition of your number of protons plus your number of neutrons, right? Now, atomic weight, right? It's that different type of mass measurement that I've alluded to a couple of times here, right? There's mass number, which again, I'm saying it, is protons plus neutrons. That's it. Nothing crazy here. Atomic mass, however, atomic weight, is something entirely different. It is a weighted average of the naturally occurring isotopes, weighted average, not just the plain old average, it's the weighted average, okay? So let's look at carbon again. Carbon is probably the most consistently used example in the conversation regarding isotopes. And there are actually 3 isotopes of carbon. There's carbon-12, carbon-13, and carbon-14. Okay, so these are the 3 different isotopes of carbon. Carbon-12, carbon-13, carbon-14. If I were to take the average, just the regular plain old average of these 3 isotopes, 12, 13, and 14, it looks something like this, right? You would take 12 plus 13 plus 14, and you would divide it by the numbers that you have. I've got 1, 2, 3 numbers, so divided by 3, and this would end up equaling 13. Okay, so that would mean that the average of carbon, weighing 12, carbon 13, and carbon 14 with mass numbers of 12, 13, and 14, the average between the masses of 12, 13, and 14, of course, would be 13, right? But why is it then that the atomic weight for carbon that you see right here that I'm circling is 12.011? As well as when you go to the periodic table and you look at the atomic mass of carbon, the atomic weight of carbon, it's also 12.011. Why is that the case? Okay, well, again, it's a weighted average. It's not just a basic average where you add up the numbers together and divide by the number of the amount of numbers you have. That's not what's going on here. Okay, it's very, very different. The atomic weight, again, it's based on the naturally occurring weighted average of all of the isotopes here. So in our entire Earth, right, on our planet Earth here, you've got different numbers, a different weight, a different average of carbon-12, carbon-13, and carbon-14, okay? We have a ton of carbon-12, okay? Carbon-12 is very, very, very naturally abundant. We are made up of carbon-12. Every living organism on the planet is made up of carbon-12, okay? There's only a little bit of carbon-13 that exists on our planet, and even a smaller amount of carbon-14 that exists on our planet here, okay? So that's why we have to take into account the weighted average. There's so much carbon-12 that exists on planet Earth that it outweighs 13 and 14, okay? And we do that, okay, we come up with this idea of weighted average by calculating atomic mass using this formula here, okay? Atomic mass equals mass of the isotope multiplied by the percentage of the isotope plus the mass of the second isotope, B, multiplied by the percentage of that isotope, B, plus mass of the isotope, the third isotope, C, multiplied by the percentage of that isotope, C, as well, right? So, and then to cap it all off, more importantly, is you divide it by 100. You do not divide it by the number or the amount of numbers you have, the number of isotopes you have, right? In this case here, we have isotope A, B, and C. So with a basic average, you would divide this all by 3, but that's not what we're doing here. That's not what we're doing here at all, okay? We are multiplying things based on the percentage abundance that we have for them, okay? And I am going to stop here, and we're going to do some examples in class, and I'll see you guys then.